It's a pleasure to be with everyone this morning. We'll get right on into the presentation. Okay, let's explore a little bit of JMv and JM fan range. Okay, so essentially this is all about our actual flow fan range and all of the variants that we're talking about. Some of it is at a fairly basic level, but it might be useful as a presentation because we will obviously be sharing this presentation with you. It might be useful when you're talking to customers or colleagues to explain a little bit more about the fan range. But you know, it kind of builds up to more complicated levels as we go through. So let's dive right in and see where we go. Okay, so what we're going to be talking about are JM fan key components and variants. A little bit about that. A little bit about axial fan performance capabilities. A little bit about aerofoil impeller blade design, and then finally some customer benefits versus other fan types as well. So we'll have a little look at all of that. Okay, so just to kind of go through the key components, this is an image actually of a JMv fan, but you know, the main components are the same. So you have a duct or housing, fan casing. In this case, it's a long casing. So you've got flanges on both ends covering the entire length of the fan impeller and motor assembly. You then have the impeller itself, and in this case, there is a spinner affixed to the hub. We'll talk a little bit more about that later. And then there are 4 mounting arms. In this case, they are also guide vanes as well to add additional performance to the fan. And then, of course, motor, which is a key component in the middle, which is joined to the terminal box on the outside via a wiring conduit in the middle there. And that's essentially it. It's a very basic kind of description, and I guess most of you might already know this, but you know, it's useful if you're trying to explain actual flow fans to somebody who's unfamiliar. This kind of diagram says it already. Okay, so now what I want to do is just have a little bit of comparison between actual flow fans and one of the other key options that we've got when we're looking at a solution for ventilation, or it might not be a ventilation, it could be some other specific application. But generally, the options that split down into centrifugal or axial, you do have variants of centrifugal fans. There is sort of something that's in between, which is mixed flow, but I'm not really going to talk about that. I'm just going to focus on centrifugal fans. So if you look at the actual flow fan features, if you list them out, you know, you could sort of say, well, okay, you've got a small footprint in the actual flow fan. It's a compact unit, really. It's easy to install and remove from ductwork because it's, you know, installed into inline ductwork, which is different to a centrifugal fan, because centrifugal fans, by their very nature, turn air around 90 degrees, which then means that unless you've got some more complicated casing, that the air enters the fan and leaves the fan at 90 degrees to each other. So obviously ductwork is a little bit more complicated in that respect. You have efficiencies for the JMv range up to 85%. When I say that, I have to be a little bit more specific. We're talking about up to 1.6 meters in diameter. There are larger fans in our range that have got higher efficiencies than that, and they're a bit more bespoke perhaps, but you know, we can achieve higher efficiencies. But I'm talking more like the standard range. And centrifugal fans, maybe I've got an advantage on that by maybe 3 percentage points. So it's not a vast difference. Generally speaking, actual flow fans nowadays wasn't the case so much in the past, but now we're talking about direct drive as a only real practical option. Belt-driven fans were something that we used to do, and in some markets it's still, you know, something that people ask for. Coupling drives are really bespoke for sort of OEM very specific applications, so they don't really get requested that often. But again, you know, if it is something that is technically possible, but it's not part of standard range. But you know, if there was enough potential for a particular inquiry, we would look at that, of course. But direct drive is really the main solution. And of course, one of the reasons for wanting a belt drive or type of solution is the ability to change the speed. Well, obviously with a direct drive solution, you can change the speed by using a variable speed drive or variable frequency drive, which have, you know, then they're much more reliable and affordable. Belt drives and coupling drives both introduce a weak spot, their point of failure, and also they have losses involved with them, which are much higher than a VSD loss. So a VSD loss could be a couple of percent, but a belt drive loss could be, you know, sort of 10–15%. Those losses for belt drive for centrifugal fans can be even higher than that. Could be 25%. So in this age of energy efficiency, belt drive is not really a sensible option anyway. So if we then look at noise levels, yeah, you can't get away from the fact that an actual flow fan runs at a high speed and predominantly creates high frequency noise. But it has to be said that if you're treating that noise with some kind of attenuation device, high frequency noise is much easier to attenuate out than low frequency noise, and it's just, you know, a factor of the length of the waveform. And then you've got in a actual flow fan adjustable geometry, you've actually got, you know, blades that you can move around to get you different performances. So it's flexible in that regard, whereas centrifugal fans have a fixed geometry impeller. So, you know, you get what you get, and the only way you can vary it is with some kind of belt drive, or maybe it's, you know, speed control. Speed control could be either by VSD or maybe it's an EC type of option. But you know, you can't do anything to the impeller, really, it's fixed, whereas actual flow fan, that's an adjustable pitch impeller. Actual fans, very good at high air volumes and medium pressure development. Not so good on high pressure development unless you go multi-stage, but you know, that's an option. Limited operating temperature, well, it depends on definition of limited, but obviously I'm talking more about aluminium impellers. So you might be limited in some cases to 300 or 400 depending on rotational speed. But you can extend those operating conditions and temperatures by using steel impellers, which is an option for us. So looking at all of those points and trying to sort of weigh up the pros and cons of an axial flow fan versus centrifugal fans, you know, what is the kind of the verdict? The verdict is that, you know, pretty much the axial flow fan is in a good place for most of those points. Slightly down on efficiency maybe, and maybe it's got some limitations with aluminium, but you know, we can address that with different impeller materials. So in a pretty good place, and also quite competitive in a lot of places versus the larger centrifugal fan offering. So yeah, a good solution for a lot of cases. If we look at the standard range, as I say, up to 1.6 meters in diameter, we're talking about this type of product for the JM range, just focusing on the JM range now, rather than the JMv, which we'll get to. As I said, adjustable pitch impellers made out of die-cast aluminium. We can have all sorts of different motor options in terms of speeds. Because of the way the impellers are constructed, we can vary the number of blades and get different performances from that. We can also vary the diameter of the hub and get different performances from the fan for any given diameter of fan. We can also create different casing variants. The one that you see on the screen is the long case, but there's also short case and plate mounted if that's more appropriate for the application. And as it stands, we've got a product that has, you know, most of its main structural components made out of steel, which is galvanized. So, you know, it's a very robust type of anti-corrosion finish. We have this high efficiency, low noise aerofoil blade section, which we pioneered in the industry. And just to make sure that the impeller solution is robust, we X-ray examine the impeller parts, because, you know, they might look great from the outside, but, you know, there could be a fault in the casting on the inside. And we are absolutely passionate about, you know, giving our customers the best possible solution. So X-ray examination is something that we do. I talked a little bit about casing options, so long case, short case. Okay, so you know, what we see on the left-hand side is the long cased option, pretty much standard for the HVAC market. And then for the OEM more bespoke option, then a short casing option is often used as being, you know, more appropriate. That reduces the length and the weight of the fan. So, you know, that's possibly a better fit for some OEM applications. Motor mounting is another issue that we kind of address. Now, I've only shown 2 motor mounting options, but there is a third, which is flange mounting, which I won't really get into. But pad mounted motors are really the most popular option that we use, and that's the left-hand side image. And as you can see, it is actually fixed to the casing of the fan with 4 mounting arms, which are equally spaced around its circumference on the carcass of the motor. And that really is a good solution as far as aerodynamic design is concerned, because obviously what you don't want is lots of blockages in the ductwork. And we'll get onto blockages and the implications of that when we get into talking about JMv. But you know, it is really important in terms of, aerodynamic performance, that we minimize the blockage and the turbulence that's created inside the duct, because turbulence will reduce efficiency, and obviously energy efficiency and increasing it in particular is very much on everybody's minds. So pad mounted solution is a better solution from that point of view. Obviously, you could use a foot mounted motor like this image that's on the right hand side, but then you've got a motor mounting platform that's underneath the motor supporting it in the lower half of the fan duct. And of course the problem with that is that you've then got extra blockage and extra turbulence being created in that duct. This particular duct is a short cased duct, as you can see, because the motor is protruding. Also, this is a deliberate mistake because this particular installation of motor, and in particular terminal box, which is quite a substantial terminal box shown in the picture, the problem with that is that it's right next to the impeller, which is a bit of a problem because it causes a lot of turbulence right next to the impeller. The airflow in this case is from the end of the motor over the motor and then through the impeller. So it's a Form B type of installation example. So we would correct that by moving the terminal box to the non-drive end, and we quite often ask our motor suppliers to do that. They can actually reverse the carcass for us before they build it, or whilst they're building it. So I just point that out. If you look at the short case fans in particular, because of the extra terminal box that's in the airstream, that does put a bit of a limit on the minimum size in terms of diameter of fan. We tend to limit it to 500 millimeters, where the losses due to turbulence are still acceptable, but below that diameter you'll get an increasing level of turbulence and impact on the performance. The performance impact is not just airflow and pressure development, it's also noise level. So you'll increase the noise level as the turbulence increases, which is obviously bad from a point of view of actual installation, because noise level could be quite sensitive or important to the customer. So you have to keep bearing that in mind. In terms of the blade design, talking about here is an aerofoil section, very similar to the aerofoil section used in aeroplane wings. In fact, the section that we use is a modified Airbus wing section, which gives a very high degree of lift, which in this case is actually gives you an airflow at a pressure rather than lift, but it's the same basic kind of vehicle. So you get an airflow in that direction if you rotate the blade in that direction. What I'm showing you there is a unidirectional fan blade section, but we do also have a truly reversible section, which looks like sort of two of those sections sort of on top of each other, but with the sort of broad end opposite. So you get a sort of more sausage shaped type of section, and that's what we refer to as a JMTSP. So it's a truly symmetrical performance, so very close performance within a couple of percent forward and reverse, and it's designed for pressure development rather than thrust development. We'll get into that a little bit later. I'm not going to talk in detail about you know, all the features of the blade, the attributes of, you know, linear and non-linear twists, but, you know, just stated for the record what the design parameters are for that particular blade section. Okay. Now, other than blade section, the other thing that really influences performance of a fan to quite a degree is the tip gap between the end of the blade and the casing of the fan. So what we've got on the screen at the moment is a kind of a representation of the impact of tip gaps. So when we do a load of testing for a range, we obviously decide what the tip gap should be as a standard. And that really is depending on a couple of things. There's the build kind of limits. So obviously we don't want to make it extremely small in terms of tip gap, because that then makes a fan more difficult to build. So you have to be practical about it. But the other aspect, which it's not really something I want to directly talk about here, but it is a factor for higher temperature fans, is that high temperature fans will need a larger tip gap, purely because at higher temperatures the aluminium blades will expand, and if you don't leave a larger gap, then the blade tip will then contact the casing of the fan and it will stop. Or worse, something will break, and then, you know, you've got a hazard there for people. Obviously, with a high temperature smoke extract fan, the last thing you want is for the fan to stop working during the 2 hours for which it's designed to extract the smoke, because its whole point of existing is to extract smoke so that people can get out of the building. So higher tip gaps are required, but the standard temperature fans have got a tip gap of 0.25 or a quarter of 1% of the diameter of the fan. So for a typical 1000 millimeter fan, it means that you need a 2.5 millimeter gap, normal tip gap. And if we do that, then you get the sort of performance that we state in the catalogue, as denoted by the red lines on this chart. Okay, so it's 0% change to peak pressure, i.e. we are giving you what it says on the chart. But obviously, if somebody builds the fan with 0.5%, so we're doubling the tip gap to 5 millimeters, then that has quite a dramatic effect on the performance, the pressure performance of the fan. In this case, a minus 16%, so it reduces the pressure development by 16%. This is why when we select high temperature fans, we make an adjustment on the performance to account for this leakage, so that, you know, the designer still gets the performance that is asked for, even with the larger tip gap. Conversely, if we were able to, and we have done this in the past as well, close the tip gap up, so we build the fan in a much more controlled way, so it's a special build, so it's only a 1 millimeter gap, so 0.1%. That would increase the pressure development by 10%. So you can see, you know, tip gap is quite an important feature of fan design. So I know I spent quite a bit of time on that, but it is quite important to the performance. So you know, and obviously the tip gap is all about this bit here. Okay, so I think we've kind of talked about that enough. The next variable in terms of an attribute of the fan is form of running. So let's have a talk about form of running. So here are the two possible options: form of running, form B, which is the standard, and I've no idea why we chose form B as the standard rather than form A. But anyway, form B is the standard, and it's air over the impeller first. So, you know, what happens is that you get air flowing over the impeller, and it's, you know, you get this is preferred because the airflow looks like that. So you start off with laminar airflow before the impeller goes through the impeller, and then you get turbulent air coming off the back of the impeller. But because it's going through the impeller as laminar flow, you get much more performance than you would if it was the other way around. Because obviously, if it's the other way around, you get a performance that looks something like that. So you get turbulent air going into the impeller because it's been disturbed by going over the motor and through the motor supports. That actually can give you a reduction of a couple of % on performance versus form B, and can increase the noise level, because obviously the turbulence is kind of energy, wasted energy, if you like, and that is exhibited quite often as noise. So, you know, that particular form B example can be 2 or 3 dB higher, which obviously is not a welcome kind of situation. Turbulence basically reduces efficiency. Okay. So looking more at the physical attributes of the fan now rather than performance. So you've got a casing, which is, you know, steel, hot dip galvanized, as say. The fixings are all built, you know, or produced in a way that they have an anti-corrosion finish, and the mix of materials for the fixings versus the casing is quite important, and, you know, in particular environments, because, you know, obviously you can get galvanic corrosion if you have the wrong mix of materials. So we have to be quite careful about that, depending on what the application is. But the idea is, you know, you have the right mix, and it repels the corrosion kind of agents, so it slows that process down. Then if you look at the impeller, which is the heart of the product, you've basically got 3 main components. I'm only showing 2 components there. You've got 2 halves of a hub. I'm only showing 1 part of a hub there, so you get a hub and clamp plate, and then you get blades, and then obviously you can put those together in different configurations. We use an LM6 aluminium alloy, which is a very good solution in terms of the fact that it's got corrosion resistant properties, because it has high silicon content. It's also relatively easy to cast into the correct shape, and it has a high stress capability. So, you know, it's a good material and proven over a long period of time. We can use a slightly altered alloy mix, LM13, which is better for high temperatures. So, you know, obviously it's more rigid for that high temperature application, which is exactly what you need, but is a little bit more difficult to produce in terms of it doesn't flow into the mold when you're casting it quite as easily. So you couldn't just standardize on LM13 everywhere. It's also a little bit more expensive. But as I mentioned before, we X-ray examine all of these components, make sure that they're good. We have a tight control on tip gaps, and, you know, the pitch angle is adjustable, as I mentioned before, so we can give the customer his desired duty. Standard balance for the impeller is G6.3, which is usually quite adequate for most applications, but you will have some applications where a lower vibration level is required, so a higher degree of balance is required, and that is possible, but it does require some changes to the fan, so it's not something that you can easily retro apply, because you might actually have to have a slightly different motor and a two-plane balancing kind of operation, but possible for the right application. So that is kind of the physical side of the fan. And I want to just talk a little bit more. This is where sort of the next part is, where a physical change to the impeller has an implication on performance. And so I want to talk about impeller solidities, which is a very odd type of term to use, but I'll explain what that means so that you're familiar with it. So what I'm going to show you now is a chart with some impeller solidities mentioned, and as you can see down the left hand side you've got a number of different hub diameters and blade options, and you can see sort of graphical representations of those. So as you can see, depending on the number of blades that you need to fit, that will affect the hub diameter, because obviously the larger hubs have got the ability to fit larger numbers of blades. And if you have a higher number of blades, then obviously you can get more airflow. Then depending on the sort of mix between the diameter of the hub and the number of blades, you can get different pressure developments. So what we're showing on the right hand side is a sort of a mixture of a particular example of impeller where you've either got one fan, so the three lower performance envelopes that you see on that chart show a single stage fan with either 3, 6 or 12 blades, and you can see just by changing the number of blades you can go from around 350 pascals maximum up to about 1000 pascals maximum pressure development, and you also increase the airflow capability as well. But obviously we can bolt two fans together and come up with a two-stage product. In this case, the two charts that are shown in the upper portion of that chart show two fans with 6 blades or 12 blades. As you see, exactly the same impeller components, but just put together as a two-stage 6 or 12 bladed variant, give you quite significant increases in pressure development. So over 1500 pascals, around about the 1600 pascals mark for the 6 blades, and about 2300 pascals for the 12 bladed version peak pressure development. So as you can see, that then makes the platform that we've got quite a flexible one. So what is a two-stage fan? What does that actually mean? Well, this in particular is what we're talking about. We actually have a situation where we've tested this out, and our experience is that if you have two fans that are identical bolted together, they give you around about 2 times the pressure development. But if you actually reverse one of the fans so that the impeller is then up against the other impeller, not right up against, there needs to be a bit of a space, and then you rotate that impeller in the opposite direction. Obviously you have to turn the impeller blades around so the angle of attack is correct on the aerofoil section. But what you then do is you give it the first stage gives a sort of a turbo boost to the second stage. So you then get a 2.7 times pressure development increase. So you actually get a kick, an extra performance advantage if you do it that way around. And that's called a contra-rotating design. And that's quite normal for our JM2 product. Okay. And a sort of a typical sort of chart that you would get, performance chart, which is showing fan total efficiencies, might look like that. So, you know, you're getting this, in this particular example, it's around about 1400 pascals total pressure, but you can get much higher pressure development depending on what you're using in terms of different combinations. But as you can see, peak efficiency is looking quite good. The 80 to 85 percent is possible. So it's quite an efficient solution as well. It's also possible where you've got a two-stage fan to provide some sort of degree of duty standby in a scenario where one of the stages fails, or if you have two completely identical fans where you get a duty standby arrangement, then we can also do that, and it has performance implications as well. I won't be talking about that in this piece, but it is a separate subject, and it is something that we do offer. So that's two-stage fans. The last thing I want to really detail out, which is something really fundamental, and I think probably most of you already know this, but some might not. It's good to sort of try and explain the code, crack the code of the product code. So this is a sort of typical code for a JM fan. So let's go through each of those parts in turn. So the 125 is the diameter in centimeters. Then you've got the JM, which is the blade designation or blade design. So that's fairly straightforward. 40 is the hub diameter in centimeters. And then you've got 4 for the rotational pulse speed, the nominal pulse speed of the motor. And then finally, you have the number of blades. Okay, that's all the sort of physical parts of it. Then you have the setting of the blade angle, and in this case, it's 26 degrees. And obviously that doesn't alter the blade per se, other than profiling of the tip. When we're building it, it does impact the performance of the fan directly. And also it may impact the sizing of the motor, because higher pitch angles require more power. So we take all that into account when we select the fan. But that's how we code the fan. So having explained the coding of the fan, the next thing to talk about is accessories. So I'm only really going to talk about the standard accessories here that most often get selected and used for the installation of the fan. So you need to somehow support the fan. Mounting feet that look like that are the thing to use. Underneath those feet, we support the fan with anti-vibration mounts. I'm showing 2 types there, a sort of rubber mount, which would be typically for standard temperature, and then spring mount, which would be typically for high temperature solutions. And then because you've got the fan mounted on a set of components, mounting feet and AV mounts that allows it to move, flex up and down, flexible connectors and clips to keep those flexible connectors attached to the fan and the ductwork are then required. If you've got that type of scenario, then to connect your fan to ductwork, you may well need matching flanges. If it's a type of mounting arrangement where you've got two fans, maybe side by side for duty standby, a damper might be needed. And in this particular example, it's an air operated damper, AOD. So, you know, obviously open when the fan runs and designed to close when the fan stops. Silencer may be required. So we talked about attenuation before. This is what a silencer looks like. In this example, it also has a central pod. So this is a C-type silencer, which is designed to take a bit more of the noise energy out of the airstream by adding more acoustic material into the silencer. If the fan is not in a situation where you have ductwork on both sides of the fan, but you've got an open inlet to increase the performance a little bit, then we would always suggest the use of a bell mouth entry on the inlet to the fan, which looks like that. And then obviously if you've got an open end to the fan, the last thing you want is to create a safety hazard. So a safety guard added to the fan, either a flatter guard that goes on that or a motor side guard the other side of the fan if it's open that side as well. So those are the standard accessories, mounting accessories that we quite often offer, but obviously, you know, there is a little bit more to it than that. So we've now got to the end of the JM bit, and we're going to move on into the JMv, which is kind of an evolution of the JM fan. Now, the JM fan was introduced a few years ago now. We're talking 1990s, and so for all that time, it's been quite an efficient solution. And when it was launched, it was market leading. And obviously, over time, competitors created their own offerings of that, and then went through, and some of them improved on that solution. So we sort of lost a little bit of ground on that, on competitors. But we're always looking to try and improve where we can, and of course, energy requirements, product directives, or regulations, which are encouraging all manufacturers to improve their efficiency. They came into play in 2013. So we started work on improving the design of the fan to try and address that. And so that's what JMv is all about, really. So let's get into JMv. Okay, so the sort of takeaway there is a massive running cost saving that we're showing there. Obviously, that's the best efficiency that we've got of running cost saving across the range. But that's quite astounding that we can offer nearly a 45% reduction in running costs, because we basically took the JM fan, put that to one side, came up with a blank piece of design paper, and then said, how do we design a fan with more efficiency in mind? So now we've got a range up to 1400 millimeters. And the first thing that you'll sort of think to yourself is, well, Andy told us previously when we were talking about JM fans, standard range is up to 1.6 meters, and now we're only talking about 1.4. Well, here's the news. The JMv fan gives you more performance for less diameter and less power. So you get more for less. So you don't actually need to have a 1.6 meter fan, because the 1.4 meter fan in the JMv range gives you very similar performance to a JM 1.6 meter fan. So we didn't really need to go to a 1.6. I mean, at some point we may do that, I'm sure, because we then offer a 1.6 meter fan, which would be giving more performance than a 1.8 meter fan of the old design. So obviously it has advantages, but it's more for less is the key thing to kind of keep hold of there. And the reason I say that is that when people are looking at judging us against others, and they're saying, give us a price and the performance for a particular diameter of fan, what we really ought to be looking at is what performance do we need and what is the optimal selection, because often the optimal selection is one size smaller. So just to keep that in mind. So what are we going to talk about in this segment? So it's going to be the range benefits for JMv, how JMv and brackets G, I'll talk about that in a second, delivers the energy savings. We did some performance benchmarking. A little bit about carbon footprint reduction and the environmental dimension. A little bit about the engineering design technology that we use, and then really what is this VCC thing, the Vortex Creation Control kind of feature that we keep talking about. So we'll go through and explain all that. Okay. So the first thing we have to say is that when we were designing the JMv range, we wanted it to do exactly the same job, but at a high efficiency when compared to our JM range. So it shouldn't be worse. It could cover all of the temperature performances that we had before. It should be, a robust type of construction. So it's a fit and forget type of solution, but it must have lower running costs for the end user to benefit from, lower fan costs for the contractor, because they're always wanting a lower price from us, and a higher efficiency, because consultants have a tough job trying to keep the energy use of buildings that are being designed down, because there is a downward pressure on energy usage and therefore an upward pressure on efficiencies that we need to use. So those are the things that we were feeling were the important things to actually look at. And so if we kind of do a comparison between the JM in 2013, 2014, when the ERP regulation 327 came into existence. So typically, if you have a fan efficiency of 70%, you see on the left-hand side in the grey panel, the motor efficiency for an IE2 motor, so efficiency grade 2 is 82% in this particular example. We have this thing called an FMEG grade, or fan motor efficiency grade, which is 70 times 82.7 times 0.82, which then gives you 57 in this particular case. Now the ERP regulation 327 target for the N grade in terms of what it needed to pass in 2013 was N grade 50. So obviously you can see that this particular fan passed that with flying colours. because it was achieving 57. However, move forward to the current iteration of the standard. So regulation 327, 2015, so this is tier 2 of the standard. That, excuse me, that had a target of 58, a pass target of 58. So you can immediately see that the example that I chose on the left-hand side in the grey panel, that would fail and wouldn't be something that we could actually legally sell in the EEA. So, you know, that's most European countries, plus the UK and a couple of other countries, such as Iceland, a couple of Nordic countries. So in that particular case, we obviously needed another solution. Now, we could have just said, well, we'll have an IE3 motor. And I know that's, you know, come into the conversation more recently because there's been a change in the motor ERP regulation. But directly the motor gets incorporated into the fan. The motor is actually just a component. And whilst we can provide an IE3 motor or even an IE4 motor, if that's, you know, what is required, this example is based on just exploring what happens if we keep the motor spec the same, but we've redesigned the fan. So the fan is now 84% efficient, the motor is exactly the same, and now the FMEG grade is 669. The pass target is 58, so that's obviously doing a very good job there. The 2022 or third tier of ERP, we still think that that grade is going to be 64, but that's still a draft. We have actually seen more recently in the last 2 or 3 months the confirmation of this. So, you know, we believe that when it is enforced, it may be later this year, but it's probably going to be in next year now. It's going to be 64. Although there is a bit of an update on that it's more likely that the grade is going to be 58. In fact, the next time it gets enforced in possibly January 2024, and then it won't go to 64 until 2026. So that, we think, is the latest intelligence on the position of the update on the standard. Okay, but you know, that's not set in stone just yet, but that's what we feel is likely to happen. But as you can see, whatever way it goes, we're in very good shape to satisfy that, both in the short term and the longer term. Okay, but the point being is that we're not reliant on the motor technology, and in fact, if we want even more performance in terms of efficiency, we can go to IE3 or IE4 motors and increase that even more if the application requires it. Okay, so just a few examples of benchmarking. Now, what I did say right at the beginning of this is don't compare size for size, because that's not really the most logical way of doing it, but you know, quite a lot of people do that. So I have done a size for size comparison here, but it's to illustrate the point that the JM fan actually has a particular performance for the size, but the JMv is always got more performance. So that kind of really feeds into my comment, which is you most likely you can go down a fan size with JMv and get the similar performance to JM. And as you can see in this example, we've got lower running costs and a lower specific fan power and a lower noise level as well. For those two examples, even though you've got more performance, you've got, you know, lower noise levels. But you know, nearly a 15% increase on airflow and about a third extra pressure. So So that's quite an improvement. If you look at the 1000mm fan, you've got a similar story: lower running costs, lower SFP and noise levels, but even more airflow, not 19%, over 19%, slightly less pressure development extra, but you've got almost a 40% power reduction at the shaft, and the running costs come down by 30%. Then we've got the 1120 size, and this is the one where it's almost 85% efficient, lower running costs, and again lower noise levels and specific fan powers, nearly a 20% extra airflow, and this 44.5% running cost reduction. So that is our sort of star size, if you like. So as you can see, that's quite a significant improvement. And then finally, the largest fan in the range, so the 1400mm fan, it was already quite an efficient fan as a JM, so we haven't increased the performance quite as much, but still at 30% extra airflow and 23% more pressure, but the efficiencies only 13.3% higher than a JM. So not quite such a big step change, but still quite impressive nonetheless. So if you then kind of think, well, what does that all translate into? If you look into operational savings, well, if you look at a typical fan that would run without major overhaul, so it would have a 12-year running life, because that equates to about 100,000 hours of bearing running life. These are the numbers. It's a huge number of kilowatt hours that you can save, and running costs, 110,000, nearly 111,000 pounds worth of running cost savings, but 624 tons of carbon saved. That's an immense amount of carbon reduction for a fan over its lifetime. If you look at the running cost of reduction, as I say, that was 44.5%. The tons of carbon reduction, this is based on all of the JMv fans that we've sold. We're getting towards 400,000 tons of carbon that would be kept out of the environment over the operational lifetime of those fans. It's enough carbon equivalent to drive 37,000 times around the world by a car, or fly 6,700 times around the world by aeroplane. So putting it into sort of more everyday terms, it's quite dramatic. Everybody kind of thinks about carbon reduction in terms of trees, because trees are used very often as a way of offsetting carbon. Obviously, because trees will absorb carbon dioxide and emit oxygen. So yeah, the equivalent is 331,000 trees, over 136 hectares or 334 acres of forest. So that's an awful lot of trees. But we don't leave it just there, because obviously when we designed the impeller parts, we looked at the material usage very closely. So based on the fact that we've got a thinner section on the blade, but it's still a very robust design because we've tested it, we've saved nearly 13 tons of aluminium. That's enough to make a huge number of drink cans, 858,000 cans, aluminium cans. So that's a lot of cans. So obviously the design process that we followed was all kind of focused on trying to get higher efficiencies and lower impact on environment, which is what I've just shown you. So one of these key tools in terms of performance was which we used, which was CFD, so computational fluid dynamics. And really, this is a way of modeling a fan in a virtual way so that we can then, you know, do a little bit of kind of a what if scenario to get to a point where we can get to the optimized design. In this screen grab that you see on the slide, the top section of that display shows a lot of red. That red is a kind of description of the amount of turbulence in the airstream, and obviously red is bad. And then we tweaked the design and came up with a more optimized design, and we produced the amount of turbulence, as you can see by the lower plot, not having any red in it. So that was a key tool. We looked at a slice through the fan, so this is kind of sideways slice. So you've got a blade and a motor support shown in the motor there. And if you imagine a particle of air coming in on the left-hand blue end of this diagram, and then traveling through the fan and then exiting on the sort of green-yellow end on the right-hand side, each one of those parts of the journeys, which we've sliced up, there will be some sort of loss associated with it. And what we've done with the JMv fan is that we've looked at each part of that journey through the fan and said, how can we improve that? And each little incremental change is added to the improvement in the loss going through the fan as air travels through. So, you know, that's what we did to minimize the aerodynamic losses. And then if you look at turbulence generated on the blades themselves, looking at a slice across the end of the fan now, so you're looking down through the fan, you can see the red dotted line, sort of that sort of shape there is showing a sort of representation of where the fan blade would be. And before the blade and after the blade, you see a red areas of high turbulence in that top plot, and a little bit of red at the tip. Now you'll see on the sort of top left-hand side, the edge of that blade is just a flat plain edge, whereas in the bottom plot, you'll see that it's got features on the trailing edge, which are known as these vortex generators. And that's where we get to the VCC, the Vortex Creation Control process that we were talking about earlier. And you can see that by putting these little features on the trailing edge of the blade, we've actually reduced the amount of red that's in that plot, which means obviously there's less turbulence. So from that point of view, obviously that means that less turbulence is good, because less turbulence means that you've then got higher efficiencies, which is what we're aiming at. So from that point of view, then let's just kind of, well, highlight the obvious there, which is, you know, these are the areas of reduced turbulence. So that's sort of more performance. But if we then look at the other aspect of this, which is the fact that we also need to make sure that the fan is as robust as it possibly can be. We use this other tool, which is finite element analysis, which is you know, a way of looking at the stresses. Here you can see a red kind of highlight kind of on the leading edge of the blade. That shows that, you know, you've got a high stress area there. We can plot the actual forces that are being exerted on the blade in different places. And we can do this in a virtual way so that we can make sure that the whole fan design is robust before we've even manufactured any physical fan. Obviously, once we design the fan in a virtual way and we then build the fan in a practical real world example, we match up the prediction of the performance and the stress levels with the model to see, you know, how well we did. And we do that by, you know, putting strain gauges on the material and actually doing a lab test. So these are the sorts of tools that we use, and all of that has gone into creating this range of JMv impellers, which have got these sort of main attributes. So on the smaller examples, we've actually got the VCC logo added to the blades, but you've got this high twist blade design that you can see, which is more efficient at low angles. You've even got, you know, a spinner that we add to some of the larger sizes. We've got tight tip gaps and tight fitting components. And in this particular case, the smaller fans have got the two-stage guide vanes. Now, the single-stage guide vanes that we use on the larger examples for the JMvG, the G is denoting that it's a single-stage guide vane. So that kind of gives you a differentiation between the two types, but they are really part of the same family. And so the key features are that the blade fit is very tight. It's, you know, it's doesn't vary even if you twist the blade around, so it's the same distance, and that's because the hub is actually curved, unlike the old hub section on the JM, which was flat and then had to have much larger kind of relief features there, which obviously create more turbulence. And then you've got the high twist blade, as I mentioned before, which gives you this excellent performance at low angles. And then these blade features, which, you know, obviously give you this this effect. Now, the interesting thing here is that these features generate vortices, which seems counterintuitive, but actually the generation of some local vortices behind, or the turbulence behind the blade in some places, actually encourages the airflow to straighten out into a more laminar airflow much quicker, and therefore it reduces your efficiency reduction overall. And then finally, you've got this spinner that we add to the front end of some examples to improve the airflow a little bit more. So finally, there is one other thing I just mentioned, and that's the guide vanes. The smaller examples have got these two-stage guide vanes, one which holds up the motor, the second one which extracts a bit more performance. Then this is the sort of range of applications that we're talking about: standard temperature and then high temperature, up to 400 degrees C. Okay, so what I'm going to do there is leave the presentation there at that point. This particular presentation slide deck, we've got to slide 51 of 90, so you can see there's quite a few slides after that. But the following slides are more to do with the rest of the range, other variants, and some application advice. So it's more of a kind of resource for people to kind of dip into if they need to know more. But as far as the presentation of the range in general and JMv in particular, that really is where I can leave the presentation.